Today, we're going to do something a little different. We're going to pull back the faceplate on some of the most famous modules out there and really get into the nitty-gritty of the invisible engineering that gives them their sound. So if you've ever patched a synth, you know these names, right? Timbre, morph, brightness. They're the controls we all reach for instinctively to start shaping our sound, to give a module its character. We plug in our LFOs, our envelopes, our sequencers, all without a second thought. But have you ever wondered what's actually happening right there, inside the jack? There's a whole world of design decisions happening that dictates how that signal gets used, and that's exactly what we're going to unpack today. And to figure this out, we're going to look at the work of a true legend, Mutable Instruments. Their modules are just famous for being so musical. And as it turns out, a whole lot of that magic is literally baked right into the hardware circuits. So first things first, what even is a macro parameter? It sounds kind of complex, but the idea is actually super simple. It just means that one knob or one CV input is controlling a whole bunch of different things under the hood all at the same time. It's the secret to making really deep digital modules feel intuitive and fun to play. And you have for sure seen these everywhere. Knobs like timbre, brightness, density, morph, all of these are classic examples of macros. They give us this one simple control to make these huge, sweeping changes to our sound. Now here's where it gets really, really cool. You would think that all these different controls would have completely different circuits, right? But after looking at the schematics for Mutable Instruments modules, a pattern emerges. So many of these inputs are built on the exact same foundational circuit. And this is it. This is the heart of the whole operation. It's called an inverting summing amplifier. I know, big name, but its job is actually pretty straightforward. It takes the control voltage you're sending in, it mixes it with the physical knob's position, and then it scales that result perfectly so the module's digital brain can understand it. But here is where the genius of the design really shines through. Even though the basic blueprint is the same, Mutable Instruments used 3 distinct flavors of this circuit, and they did it just by changing the values of a few resistors, tailoring each input for exactly what the module needed to do. Okay, so first up is type A, the standard bipolar input. Bipolar just means it can handle signals that swing both positive and negative. This one is set up for a plus or minus 5 volt signal, which is super common for things like LFOs. You'll find this design on inputs like model on plates or texture on clouds. Now let's check out type B. This is the extended version. Just by swapping out those resistors, this circuit can now accept a much wider plus or minus 8 volt signal. This is for the parameters that you really want to modulate dramatically, things like the timbre on plats or the main controls on rings and elements. And finally, just to complete the picture, there's a type C. This one's a special case. It's unipolar. That means it's only designed for positive signals, from 0 to 5 volts. This is perfect for parameters like position or density on clouds, where you don't really need a negative modulation. Okay, so we've got these 3 different input designs. But so what? What does this actually mean for you in the real world when you're making a patch? What happens when you plug a signal meant for one type into a jack that's built for another? Well, this slide shows it all perfectly. You've got 2 basic mismatch scenarios. If you send a big 8-volt LFO into a type A input that's only built for 5 volts, your signal gets clipped. The hardware literally just chops off the top and bottom of the wave. But what about the other way around? If you send a smaller 5-volt signal into a type B input that's ready for 8 volts, it works, sure, but you're not using the full range. You're effectively losing about 40% of your sonic detail, your digital resolution. And look, here's the cold hard data. You can see that clipping right here in the numbers. As soon as the input signal goes past plus or minus 5 volts, the output voltage just hits a wall. It flatlines. Those beautiful expressive peaks of your modulation, they're just gone. That musical information is lost forever before it even gets to the brain of the module. All right, so the voltage range is a huge part of the puzzle. But there's another piece to this, and it's just as important: speed. How fast should a parameter be able to change? Is it always better to be faster? This, my friends, is the secret sauce. A tiny little component, a feedback capacitor, gets added to the circuit. What this does is turn the input into a simple low-pass filter. And the value of that tiny capacitor is a very deliberate, very musical choice that helps shape the whole identity of the module. And this is a perfect example of that musical choice. On one hand, you have plates. It's an oscillator. It needs to react instantly to make sharp, plucky, percussive sounds. So it uses a capacitor that allows for lightning-fast changes. But on the other hand, you have rings, a resonator. It's supposed to sound like a physical object, and those things don't just change their properties instantly. So it uses a different capacitor that filters out more of the high-frequency changes. This makes the response smoother and less noisy. It's a conscious trade-off. Do you want more detail or a smoother response? So after digging through all of this, the voltage ranges, the filtering speeds, what's the ultimate takeaway? If you were sitting down today to design a brand new module, one that's super flexible, what would be the best way to do it? It really comes down to two main rules. First, you'd want to use the type B circuit, the one that can handle the full plus or minus 8-volt range. Why? Because you can't get back information that the hardware has already clipped off. It's just gone. And second, you'd use that faster capacitor. You can always slow things down in software later, but you can never, ever add back the high-frequency detail that the hardware has already filtered away. And this all brings us to the core thesis, the big design philosophy we can pull from all this analysis. It's simple. Design hardware generously, restrict in software. You build your hardware to capture as much information as it possibly can, the widest voltage range, the fastest response, and then you use the power of software to shape and constrain that for musical purposes. It's brilliant. So the whole point is this. Every time you patch a cable, you are interacting with a whole chain of these incredibly thoughtful design choices. So the next time you turn a knob, think about those hidden circuits working behind the scenes. And ask yourself, what other invisible decisions are shaping the sound that I'm making right now?